So now that we've introduced the displacement current, we have all the pieces together to arrive at Maxwell's equations, as stated and written on t-shirts and things like that. Before we start, I also want to point out that there's this other person, Heaviside, who did a lot of the subsequent rearrangement into the way that we see them right now. Heaviside was an engineer who was, I guess, too much of an engineer to receive proper credit among the physicists and mathematicians, which is why I like to bring up his contribution to organizing these equations in the consistent way that we know them right now. Another contribution he has that has made our lives better is you might remember the trick of partial fractions, where if you have 1 over, I don't know, x plus a, x plus b, he gave what we would call like the cover-up approach to if you needed to separate these into two fractions. So that's another contribution that he made. Like I said, things that make your life easier, but may not be super hardcore science-y and win Nobel Prizes. So he died penniless and underappreciated. So let's take a moment to appreciate him. But now that we brought him up, let's move on to what Maxwell's equations looks like. So the goal here is we're going to tie all of the equations that we've learned so far into one glorious slide of equations. And if you follow all of the laws here and look through it, I think you'll be in really good shape. You'll have a nice global picture of everything that we've learned so far in the electrostatics, magnetostatics, and now Maxwell's equations portion of the class. So to start out, we're going to list the laws here, but we're going to also write them out in different forms. So we'll start with the integral form. And then we also have the differential form, sometimes also referred to as the point form. And then separately, because we're going to talk about this later, but we can also write about this in terms of the Phasor form, right? So by phasor, we recall what phasor means is that we assume that the electric field is a sinusoid, so it can be described as some kind of E naught e to the j omega t a, and h is also going to be the same thing. It's going to be some kind of h naught e to the j omega t b, because they're perpendicular, so these will have different unit vectors. But that also means that when you take the derivative, it would be the same with respect to time. Instead of d by dt, whenever you do d by dt, it's the same as multiplying it by j omega. Right? So let's march through the various equations. So first of all, let's start with Faraday's law. So in integral form, Faraday's law is Ampere's circuit's law, in the sense that you have a closed line integral of E dot dl, or is Kirchhoff's voltage law, where if you take a closed line integral of E dot dl, in the case of electrostatics and magnetostatics, you would have 0, right? Kirchhoff's voltage law says that if you integrate around a loop, you would get 0. But if there's a changing magnetic field, the change in if you have a changing magnetic field, then the change of the magnetic flux with respect to t is going to give rise to the electromotive force, right? And then in differential form, the closed line integral of E, if you shrink it to a point, will be the curl of E is going to be equal to minus dB dt. And then in phasor form, we just replace d by dt with multiplying it by j omega. So that's going to be equal to minus j omega b. Next, we have Ampere's law, which is the closed line integral for a magnetic field. And in our case, when you take a closed line integral of a magnetic field, what do you get? So you get the current that goes through it, right? So surface integral of j ds around that closed surface. So again, just to illustrate that, if I do a line integral around in this circle, it would give me the total amount of current density going through that. And then plus what? Plus our new discovery of the displacement current, right? So also the surface integral of d by dt electric flux density ds. So there are two terms here. There's no similar term here because there's no magnetic monopole. Next up, if we take this into the point form, the line integral turns into curl. So the curl is going to be equal to, you take out the surface integral, it's going to be equal to j plus the change in electric flux density. Similarly, if these are phasors, the curl of h would in turn just be j omega d. So note that usually I'm leaving out the j term here because usually when we're talking about phasor forms, the main motivation is to start talking about propagating waves in a source-free situation. So since we're just looking at how the wave propagates and there's no source, we just set j equal to 0. So for the purposes of looking at it in phasor form, we're just going to look at the time, the d by dt of d, in which case the time derivative ends up being j omega. And then the missing names is Gauss. So we have Gauss's law, specifically the electric field version is the form which we first encountered Gauss's law, which is saying that a closed surface integral of the electric flux density. So if you add up all the arrows coming out of a closed surface, what you end up getting is the charge enclosed. As in, like, if you add up all the arrows going into and out of a closed surface, you get the number of arrow generators or arrow sinks inside. The point form of taking a closed surface integral would be the divergence. So the divergence of d is going to be equal to the volume charge density inside. And again, in the case of phasors, we have the divergence of d, but since we're talking about propagating waves in this situation, we're looking specifically at the source-free scenario. So we're going to assume that the divergence of d is going to be equal to 0. And then finally, we have Gauss's law, the magnetic field version, which we didn't really explicitly state, but you get the general idea, that magnetic monopole concept. So if you add up all the electric flux, the magnetic flux going into and out of a closed surface, what do you end up getting? 0, right? Because there's no such thing as a magnetic monopole. So all the arrows going into a closed surface will be equal to the arrows going out, and the closed surface integral is going to be 0. And similarly, the divergence of B is also going to be 0. And that's the case for the source-free phasor form as well. So let's just take some time and write out specifically if it's source-free and not in phasor form. That means that there are no currents, no charges, in which case our relationship is a little bit more simplified, where we have the divergence of E is going to be equal to negative the change in magnetic flux density. The divergence of H, the magnetic field, is going to be the change in electric flux density. And then the divergence of both E and B and H end up being 0. Or these can be D and B as well. They end up being the same thing since they're just multiplied by a constant. So this is Maxwell's equations. So Maxwell, with some help from Heaviside, combined all this into this set of equations where they have where you can see the symmetric relationship between the two, and it ties together electric field theory and magnetic field theory. And while we're summarizing these equations, let's just also write out key relationships. So other key relationships. So the electric flux density relates to the electric field through the epsilon parameter. The magnetic flux density relates to the magnetic field through mu. And then separately, remember, the current density also relates to the electric field, right, in a conductor through the conductivity sigma. So these are other key relationships that go into, the relating B and H, E and D, as well as J and E. And then separately, to wrap up, let's also quickly review the boundary conditions, which also has their own source of symmetry. Right? So in case of electric fields at the boundary, the tangential component is always going to be continuous. But the normal component, if there's any difference in the normal component, it can be made continuous through the charge density that's at the surface, right? And magnetic fields, it's kind of the opposite, right? So you have the tangential component of the magnetic field. If it's not continuous, it can be compensated for by what? By the sheet density going out of that at that interface, right? But then separately, because there's no such thing as a magnetic monopole, that means that when we do the surface integral equivalent, which is how we relate the normal components, the magnetic flux density is going to be continuous at the boundary, or the normal component of the magnetic flux density is going to be continuous. So with that, we have the full set of Maxwell's equations that describe the electric field and magnetic field and how they relate to each other. So we have them both in integral form as well as point form. But over here, just to quickly summarize, Faraday's law describes how a changing magnetic field can create an electric field. Same in differential form. Remember, the line integral turns into a curl when you're doing a differential form. And then similarly, Ampere's law tells you how a changing electric flux density, as well as a source current going through a region, can create a magnetic field, right? And then similarly, that closed line integral turns into curl when you're looking at it in point form. Separately, there's Gauss's law. If you apply that to the vector fields, so the flux, if you apply it to electric flux, you'll see that when you take a closed surface integral or take the divergence at a point, you end up finding the total charge enclosed, or the volume charge density. Whereas in the case of magnetic flux, because there's no such thing as a magnetic source or a magnetic monopole, these closed surface integrals are going to be zero. We also introduced the Phasor form, where it's the same as the differential form, but it will help us quantify propagating electromagnetic waves further down the line. So I'm just going to write it here so that you have some extra exposure to the equation in the context of the other forms that we've put up. And the main difference is that we assume it's source-free, so there's no J, and then separately that they can be written in the form of this Phasor form here. So if you take the time derivative, it's the same as multiplying it by j omega. And really, that's the main difference between the Phasor form and the differential form, right? So there's no source, so there's no charge, no current, and then separately, d by dt operators turn into multiplications of j omega. And then finally, we also have the key relationships where electric flux density is related to electric field through epsilon. Magnetic flux density is related to magnetic fields through the permeability mu. And the current density is related to electric field in conductors through the conductivity parameter sigma. And then over here, we have the boundary conditions where they kind of have kind of offset symmetry, where in the case of electric fields, the tangential component is always continuous. For magnetic fields, it's the normal component of the magnetic flux density that's always continuous. And then in the other component, so in this case, electric field density, the normal component, if there's any discontinuity, it can be harmonized through charge density at the interface. And in the case of magnetic fields, if there's a tangential discontinuity in the magnetic fields, it can be resolved by having a sheet current density on the interface. And so that ties together all of the equations that we have so far describing Faraday's law in electric fields and magnetic fields. And now you know everything.